a realization of single qubit POVM via one-dimensional photonic quantum walk. It's not a topic that I'm very familiar with, but like if there are some physics people, I'd appreciate if you give your opinion on some of the concepts. Uh, and so yeah, like this paper is more like it was interesting for someone uh, like an experimentalist and both theorist. So what they did in this paper is they kind of realized a single qubit POVM and used it like experimentally realized it in a photonic architecture, and they used it for non-orthogonal state identification, like the state discrimination of like non-orthogonal quantum states using like quantum walk. So, what I will be talking about in this session is first I will just give a very brief description on quantum walk, then on POVM and its significance, and like next I will just show the example that was used in the paper and unambiguous state discrimination through quantum walk and the experiment they designed to realize this example, and the next how to generate the SIC POVM through quantum walk, and then finally I would wrap up. So to begin with, like what is quantum walk? Quantum walk is it's just a quantum mechanical analog of the classical random walk. So just classical random walk is we have a two state, like a Walker state and the Coin state. Then like the Walker would be described by a certain probability distribution and for example, in a one-dimensional case. So if we see like the classical random walk, we might have a Walker state, and then just by flipping a coin, we just might need to go to the right or to the left. This picture seems to be very descriptive. Uh, so we just toss a coin, and depending on the outcome of the coin toss, like the Walker moves to the right or to the left. So like we can just expect this to be Gaussian, the distribution for the classical random walk. But in the case of quantum, like it gives an intuitive distribution, like because of the superposition. We might for example, here, when we define a quantum walk, we have two states, the Walker state and the Coin state. The Walker state is defined in infinite dimensional like Hilbert space, and the Coin state could be a two-level system, such as the qubit, like a computational basis. So if we had apply Hadamard on the zero state, we create the superposition, and then if we define a shift operator that shifts the position to the right if the state of the coin is zero, and that pushes like to the left if the state of the coin is one, we can get this description of the state if you're applying it to uh, in the case of the quantum. So this is like just the idea behind quantum walk. So like when we design our algorithm, it doesn't have to be always Hadamard, but we can apply this coin rotation depending on the state of in the position of the Walker. So there could be a non-trivial correlation between the Walker state and the coin state. So if we do some sort of measurement on the Walker state, we might be able to determine or get some information about the state of the coin. So yeah, that's the idea that they're trying to like use in this paper. So if we see about, oh, okay.
Can you explain the unintuitive distribution?
Okay.
The reason why the
Yeah, this distribution. Okay, so like if classically if we expect, for example, if you are at the origin and then you flip a coin, there's a 50% chance of turning to head and tail, right? So that after, like, for example, maybe 50 walks, there will be high chance you'll be at the origin, right? Because there's 50% chance of going to the right and 50% chance of going to the left. So, but since it's like also a random phenomena, but there's small probability of being at maybe at a position 5, or but like you won't be at a position 50 after 50 walks. Like the probability would be decreasing. So we can expect it to be Gaussian for the case of the classical, but for the quantum, let's say we prepared a superposition state, and then we apply a shift operator. So like both in both direction, you'll be going in both direction, and so like so that there's because of the superposition case, uh, like there will still be a particle like this particle at certain point, and like it won't return back to the initial or the origin point just deterministically. So there's some probabilistic case in this. Okay.
I could understand the shape of curve became like this by your explanation, but
Okay.
I can't understand why it has this shape.
Okay, the spikes. Uh, Maybe actually I took this picture from. So it's okay. Position is shifted based on. Okay, superposition. Yeah, I'm not sure if I could give you like very, maybe like yeah, I'm not sure if I could give you like really, but that's why maybe it's said like the distribution would be unintuitive. Like maybe we cannot explain it. Yeah, but like yeah, I'll try to like if there is any reasoning behind this kind of plot, and I'll tell you. But yeah, it seems to me hard to explain it why. Yeah, maybe I cannot give you like a satisfactory answer for that, right? Okay, and let's see about POVM. Uh, like just POVM is a generalized version of projective measurement, and it gives like more information from single measurement than the standard Van Neumann projective measurement. So realizing this POVM is like important and significant. Or like mathematically, we can represent it as like a summation, like just an operator that satisfies these conditions where the summation of each uh, is summed to be identity, and outcome from a certain POV measurement we be given by trace of this. So a good thing about POVM is that it would give us like it would allow us to distinguish two states that are non-orthogonal. For example, if you want to distinguish two non-orthonormal states, like if you design, for example, the Stern-Gerlach measurement, you might not be like always accurate, but at least if you do like the POVM measurement, you might be able to identify correctly, but there might be some cases that you can get inconclusive results. So yeah, that's one problem that POVM measurements could have an advantage in this distinguishing non-orthonormal states. So and like the other is so using quantum walk, how we can like make a generalized measurement. So yeah, like maybe in the trivial case, we can just think it this way. So let X be the Walker state and 0 be the state of the coin. And like depending on the position of the state, we kind of shift the Walker. And if the like state of the coin is 1, the Walker is going to be shifted to the left. So if we do measurement on the like the Walker, the on the like on the Walker, then and if we get the particle at x equals to x plus one, we might be able to infer that the initial state of the coin was zero. Just trivially, we can just see it this way. So for a more complicated case, we can design this algorithm to be maybe applying a certain coin rotation at a certain point, and then like infer the state, the initial state of the coin by just detecting or by uh, doing measurement on the Walker state. So yeah, that's how we realize uh, like unambiguously discriminate states using quantum work. So yeah, like the experiment or the example used in the paper was to unambiguous state discrimination through quantum work of a certain state. For example, we have state phi. Let's say we have two states, phi plus and phi minus, and we want to discriminate two states. Like for example, we have, let's say that we have a source, and that source produces phi plus and phi minus with equal prior probability, and we want to know whether like our given state is phi plus or phi minus. So in order to do that, they like realize or do these experiments through on a photonic architecture, but theoretically it's like this. So we can just do this state discrimination using a three-step quantum walk. So how do we do that? First, uh, we have the state phi plus or phi minus would be the state, and there would be like a Walker state that would be at the origin. Then what is going to be done is we apply coin rotation based on the state of the Walker, like site. It's called a site dependent coin rotation, and there should be also a shift operator. So what this site dependent coin rotation does is, for example, C12 is in the next step. If the Walker is at a position x equals to one, you do this unitary operation on the coin state. For example, in the second step, for example, in the like at the zero step, like it will be at the origin. So C0 of one is going to be identity. You don't apply anything. Uh, then you do the shift operator. The shift operator is going to like shift the Walker to the left if it is uh, one, and to the right if it is zero. Then you apply, if it's at position x equals to one, you apply this operation. If it's at minus one, you apply this operation. Then in the third step, if it's at three, then you apply this operation, else like you apply identity. Then finally, you get a certain state of like these two composite system. Yeah, like finally at the third step, you get a state like a state of the Walker and a state of the Walker and the coin to be somehow entangled. So what you're gonna do is to measure the Walker and then uh, tell about what the initial state of the coin was, whether it was phi plus or phi minus. So in order to uh, realize that, they used this kind of experimental setting. So they generated a single photon and pass it through a beam splitter uh, to encode the coin qubit as like using the horizontal polarization for the zero state and vertical polarization for one state. So I'm not sure, like very familiar with these optical equipments, but the Walker position was realized through a longitudinal spatial mode. So after passing through this, there's something called the displacer or something. So like the photons at this position, it corresponds to x plus one uh, uh, Walker's position, and these are the like site dependent coin rotations. So these are like half wave and quarter wave plates. Just put it in a certain angle so that they are used to realize these site dependent coin rotations. So if it's at one, you use this coin rotation operation. like using some photonic equipments. Then finally, there could be any detection at x equals to -1, +1, or +3. So depending on that, we will be able to tell whether this initially prepared state was phi plus or phi minus. Yeah. So like theoretically, how it does look if we do the calculation, for example, from this equation by just matrix multiplication, and we have this state, and then we apply this operation here, and then finally we can calculate the state exactly after three quantum walk. If the state was initially phi plus, then the state after 3 walk is going to be like this. If the initial state was phi minus, the state after 3 walk is going to be like this. So if you do measurement on the walker, and if you detect the particle at, if you detect it at a position x is equals to 3, then both has a probability of being detected there. So we can say the result is inconclusive. But if we detect it at x equals to 1, we can just for sure say that the initial state was phi plus. If we detect it as -1, we can for sure say the initial state was phi minus. So this is the results they get from these experiments. So if we see here, like both of phi plus and phi minus, they're exactly the same for x equals to 3. So this corresponds to the inconclusive result. But if you get this, they got this result like only x equals to 1 for phi plus, but only at x equals to -1 for phi minus. And the other result they get is like there's a certain like sometime you might detect it at x equals to 3. So this is inconclusive result. If it's inconclusive result, we say just that's kind of maybe a failure or error. So that is determined by how close are those two states. For example, if they are orthogonal to each other, then phi would be 90 degrees. So this inconclusive case will happen with zero probability. So when you increase the theta, like the phi angle from 45 to 90, the probability of these inconclusive results to happen goes down to zero. So yeah, so the experimental and the theory verification was like kind of satisfactory, and just the results were accurate. And in order to evaluate the experimental performance for this setup, they used this metric, and it shows that really a good agreement between the theoretical and the experimental results. So that was for like an ambiguous state discrimination, and like they used a 5-step quantum walk for generating a single qubit SIC POVM. So SIC POVM is, of course, it stands for symmetric informationally complete POVM, and it corresponds to a set of projection operators that are with the vertices of a regular tetrahedron. So these are not unique because if you kind of rotate them, like you can find other SIC POVM elements. And like, so if you choose these SIC POVMs to be these, for example, this one, satisfying this condition, and you prepare a coin state to be on orthogonal of something that is orthogonal to these SIC POVM elements, then initially we can represent the like the Walker state to be like the coin Walker system to be like this at the origin and the initial state. Then same way that was done for the previous case, we apply side-dependent coin rotation, and then after 5 steps, you get this kind of after 5 steps you get this state. If you do even like the calculation by multiplying the matrices for each if we do the calculation, we be able to get these states from each initial state. And then what we can observe from this is that, for example, if the initial state was 1, you won't be able to get you won't be able to get the Walker position at a position at certain position, like maybe 5. So you won't be able to detect it if it is 5. If it's 5-1, you won't be able to detect it at 1. So it's kind of corresponds to that, like realizing the POVM element, because if you see, maybe like you'll be able to see it from their experimental result here. What they get from the experimental result is that if the initial state of the coin was at psi1, then the probability of getting it at 5 is very low. And then if it's psi2, the at 3 is very low. So like you'll be able to tell which state was in the beginning by seeing this probability. So yeah, this corresponds to, because if we have like all the POVM elements, and then like if you're using it on something that is orthogonal to that one, there will be, you get a probability of 0 of detecting that state in the orthogonal state. So this, from this result, we can tell that with all the SI, we can successfully realize the SIC POVM elements. So finally, limitations and something challenging part of this experimental realization of the SIC POVM. So what is good about this thing is quantum walks are like they're stunningly powerful approach for quantum algorithms, and they have like a wide range of applications, and even in machine learning algorithms. But there is only problem in physically realizing them. There are some problems, like because when you use the photonic architectures, photons, they doesn't interact easily. So, and applying to two cubic gates, or like on a two systems, could be difficult in the case of photon architecture. And the other problem is like this was only realized on one-dimensional case, but if we want to extend this to a bigger problem, we also need to like extend the dimension to higher, like we need to extend the physical dimension when the complexity of the problem is getting bigger. Yeah, so these are one of the limitation, and they have also some powerful advantage. So thank you. That's all. If you have any question, welcome.
Thank you for the presentation. And can you go back to the slide that shows POVM element?
This? Which?
Yeah.
Here?
Yes.
Okay.
It's kind of elementary, but can you explain how to get the coefficient?
Here? Yeah, actually, yeah. First, when you like maybe here, it looks like this is in order to discriminate those two states. These were like designed in a way to be orthogonal to phi1 and phi2. They seems to be orthogonal, but I'm not sure how where these coefficients comes. But for E3, I think it's maybe, is it normalized? Yeah, from the like this normalization, but I'm not sure if
maybe that's from the condition that E3 is typically positive operator.
Oh yeah.
I think there might be upper bound to the that's a guess.
Yeah, like they have to be, there are some conditions for these operators, right? They have to be like a positive semi-definite, and they have to satisfy this condition. Maybe I'm not sure, but like from that, I'm also not very familiar with these topics.
If we have,
Okay.
we have some range to determine this question, then that means we can just probability of measuring the state.
If you like, I mean, you mean okay.
If the coefficients are determined
Okay.
due to the positive semi-definite condition, then I guess we have some range to define the coefficients, right?
Okay. Then they don't. Do they exactly need to be these values? I'm not sure. Okay. This is the maximum value. Okay, but so they could be different values too, right? Okay. Okay.
So it is determined to probability of history list.
Okay, so like there's an inconclusive case, right? Where like there like sometimes you can like tell whether it was phi1 or phi2 exactly, but so in order to minimize that state, so you adjust the coefficients of this. Okay, see. Oh yeah.
I was wondering if there's other ways of implementing some arbitrary single-qubit POVMs in these photonic architectures.
But like you realize them by just adding some ancilla qubits and just doing some like unitary evolution and making measurement on. I'm not like really sure, but it's kind of this is just also using the Walker state as a. So yeah, like that's how it's implemented, physically realized, right? So you mean on photonic architecture, if there is any like other way?
Yeah, so you introduce one way to implement these POVMs in photonic architectures, but is there another way to do it? And are there pros and cons to these different methods?
I'm not sure if like I don't know. This is the only way. Just it's kind of like introducing quantum walk and then using quantum walk just to realize the POVM elements. But I'm not sure if there is. I don't know. I don't know about that.
Also, maybe I've missed, but is quantum walk hard to calculate? Let's go.
Quantum walk hard to calculate because I mean there is some sort of entanglement, right, between the those two, the Walker state, and so I mean like I think because will it be easier? I'm not sure. Because like you're trying to maybe it's maybe like this is not in terms of like computational, but it's just physically maybe it's just more of not like a computational thing, but you have some source and you want to know about that state and realize the POVM elements. So it seems for me like too much physical then. Yeah, we're just trying to know about like the certain quantum state. So yeah, like we're not computing about some like some quantity or just doing some application. But Thank you. That's it, right?